Okay, it's 3 o'clock, so we'll get started, okay? So today we continue our graph and the graph algorithm discussion. And we just started to a graph. Graph had the edge and your vertex, okay, versus vertex, the basic definition. And then we cover that you can use a two-dimensional array to talk about the adjacent matrix, or you can use a vector or vector for it. Okay, so this one we covered. And then we talk about the possible using adjacent list. So each node have different edge on the to each the neighbor nodes. Okay, this is called adjacent list. This usually is a vector of the node or pointers. Okay, so these are the basic representation for the graph. After the basic representation of the graph is done, we talk about this word later problems. Word later problem given the idea of you have some word and these different words. We just choose a one later change path to go through the network to find out from a word full to a word sage, and then where on the network you can go through there. So we do have that. And then we cover the breadth first searching and depth first searching. Okay, there's a basic searching. Basic searching means that using the graph and you use the widget vector, and then you go through the graph to go to do traversal on your graph. Okay, that's a traversal on a graph. You have breadth first traversal and depth first traversal. Okay, so these are the order we cover this chapter. And then today we are going to continue to do the traversal. But the traversal we are going to introduce today will be Dykes algorithm and Prim's minimum spanning tree algorithms. Okay, so these are two more. So we build a graph using adjacent matrix or adjacent list, right? And then we have the depth first searching or graph depth breadth first searching, two different searching way. And then today we add two more searching way. One is minimum spanning tree, MST, minimum spanning tree. And the other one is Dykes shortest path problem. Okay. There are others like strongly connected component, whatever. Okay. But those we'll discuss later. Today we focus on the spanning tree part and shortest path part. Okay. Now let's go back to this one called graph theory given by the gateway. Okay, so have a graph. You have a representation of the vertex and edge sometimes is only the connection of the two nodes. Sometimes you have the weight on it. So this one is connection, only the connection, but no weight. Okay, no weight one, no direction, no weight one. Okay. And this is the basic representation. But sometimes the edge have the direction and may have a weight. Okay. This different problem, we'll talk about it later. Right now, I don't talk about problem, I talk about the data structure first, okay? Still how to store the graph first. So now there's a directed graph, okay? You also have the directed graph. Now, next idea you need to know is actually path. Okay. Path in the graph is that when you from 4 to 6, you go from here to here to here. This actually is a path. Okay, this is a path from vertex U to vertex X. Okay, and you try to go. So path is also when you have the depth first searching, you search from somewhere to somewhere. Okay, you from a beginning node and then have to the ending node, and you do depth first searching. That's also a path, but you actually search many paths so that you go through every possible node. Okay. And this path sometimes you actually, so this path can be a path from your searching tree, from the depth first searching tree. That's one path. And it might be have other definition, but as long as you have a source and you have a sink, then we call it a path. Okay, we call it a path. This is just basic definition as a path. Okay, this is adjacent matrix and adjacent list, we talked about it already. Okay. Connectedness, actually, there are also algorithms. You need to check whether, say, 4 and 5 are they connected or not? Okay. Or where can you add a single edge that you connect the 4 and 5? Okay, so there are problems like that. Okay, but that's connectedness. And some partial graph, we call it subgraph. Okay, we call it subgraph. And tree is a special graph. Okay, these are just a basic terminology. And we call it complete graph is every node has every other node as its neighbor. So this is a CNP2. We call it complete graph. That's K-graph problem. Okay, in AP we covered this already. And graph can also have biparty, if the vertex divided into V1 and V2. Okay, and there's no such that there's no edge between the two vertices or two vertices of V1. Okay, so you actually have certain internally you don't have edge. It's just something that you actually cross the party. But internally in V1, each other don't have the neighbor. V2, you don't have neighbor. That actually is called priority. So if you cut all the edges, you divide that two group into totally unconnected groups. Okay, that's called bipart. Okay, these are just concept. We just want to cover this basic concept. So now that we will go back to the problem of the shortest path problem and the find minimum spanning tree. So we will get started from minimum spanning tree. Okay. So this is a minimum spanning tree. We'll look at this one, GIG. Okay, this is GIG. GIG has this prime algorithm for minimum spanning tree. So there are two spanning tree algorithm. One is prime minimum spanning tree. The other one is Google's minimum spanning tree. So we'll talk about these two versions. Both are greedy algorithms. Okay, both are greedy algorithms. So greedy algorithm is that based on your greedy idea, the something that you pick, you look at locally that's actually is minimum or maximum, but you add it to the set that will still be the optimal solution to the total problem. That we call it greedy algorithm. Okay. So the algorithm will actually when you do minimum spanning tree, first one that what is the minimum spanning tree? Okay, spanning tree means that I do have a graph. Okay, maybe like this. But if I started from a certain node, I want to build a tree so that every node is connected. Every node is connected. Then this tree, this connected tree, we call it spanning tree. Spanning means that from this point, you can reach every other node using the tree. Now we call it minimum spanning tree. And the spanning tree that has the minimum weight on it, then we call it is minimum spanning tree. Okay, that's actually the definition of minimum spanning tree. So first spanning tree is the tree that connected all of the components. We call it spanning tree. And the tree that has the minimum weight on it, we call it minimum spanning tree. So this one, sometimes you actually need to find such a problem. So there is an algorithm called Bloom's algorithm. Okay, so initially, you starting with an empty spanning tree. Okay, and then the idea is that you actually divide the set into two sets. So first set containing the vertex that already been included. So let's assume that you have this 5 node or 6 node. Okay, let's assume you have this 5 node. And you pick this node as the set number 1. You only have this, so this is A, B, C, D, E. Okay, so let's assume B is only node that you select in the node, right? And then you start each step, you consider that all the edges connecting in the group 1 and group 2. Group 2 actually right now have A, C, D, E. That's actually your group 2. So you will look at the edges that across the group 1 and group 2. So at this moment, group 1 and group 2, the edges that cross over it is actually all of the connection on B. So you actually check these 3 different ones and you pick the minimum one and you connect it. That's assume that to A is minimum one. That's assume it's 1. So A, B are connected. So the next step, you are going to actually pick all the edges that connected AB and then outgoing from AB and then it connected to the other node. So you check your AB and check all the edges that had not been used, not including AB, all other edges. Which one you actually give you the minimum weight? That's so this is 2, so you pick that one. And then you add that edge into it. And then next one, you actually have the ABC that are connected already. So from ABC's outgoing edge, but you cannot use AB and AC because AB, AC are not outgoing. So you will figure out, and BC are also not outgoing. So you only have BD and the CE to check which one has a lower weight. Let's assume that B is a lower weight and you connect it. So keep doing that until every point is actually being connected. Then you will have your minimum spanning tree. And this algorithm is called Prime's algorithm. Okay, this one is called Prime algorithm. So any questions so far? This is the basic idea. Is that okay?
Yeah.
And not really hard, okay? So let's look at this network from here. So basically, let's actually get started from a 0 point, okay? And then there's a weight of 4 and 8. So you outgoing node 0 only have these 2 edges. So you pick 4, that's actually minimum weight. Okay, and at there, then your 0 and 1 are connected. So your outgoing edge right now would be 8, 11, and 8. So you pick one of the 1, 2, or 0, 7, it doesn't matter, okay? So that's so you pick 7. So now you have a node 1, 0, 1, 7 are all in the group. Now you pick an outgoing edge. Right now you have 8, 7, and 1. So you pick 1. Okay, and then 6 is connected. After 6 is connected, now you have 8, 7, 6, and 2. Okay, this is the cut. This is the cut. So you pick 2. So 5 is connected. So after 5 is connected, now your cut is right here. You have these different nodes. Okay, so you have 8, 7, 6, 4, 14, and 10. So you pick 4. So you actually pick 4 and 2 is connected. Now, the outgoing edge right now is the 2, 7, and 2, 7, 6, and 7, 14, and the 10. Okay, these are the cuts. So you will pick 2 to connect it at node 8. Okay, that's okay. And you got this. Now, this one, your outgoing edge right now is 7, 14, and 10. So you will pick 7. Okay, and then your node 3 is connected. Now, only 4 is left. So your outgoing edge would be 9, 10. So you pick 9. And after you pick 9, then you actually completed your minimum spanning tree. You should have a tree that actually look like this. Okay, this is the tree that you have. That's your minimum spanning tree. Okay, so right here there is a code. Let's actually look at the code, okay? Okay, so this minimum span tree, let's look at it. So it actually is included its bits standard C double plus H. Okay, these are the competitive programming library. Okay, that's okay. Now you have a function that's called min key. Okay, so you have vector of integer as key, and then there is a vector of Boolean. Let's say minimum spanning tree sets. Okay, so this minimum spanning tree set, this one I think is representing who is in, who is out. Okay. Okay, so you pass these two values in there. So you utility wants to find the vertex that with the minimum key value from the set of vertex that's not included in the. So this one is you actually your set is the graph that you already been connected. And then based on that set, you try to figure out who has the key value that actually is the minimum, and you will add that into your minimum spanning tree set. Okay, so that's called min key function. So here you have in max, that's the minimum and minimum index. Okay, these are the number, know the number. Okay, and then value is this. Okay, the know the number is mean index. So eventually you will return the mean index that the node is vector index. Okay, so you go through the every set. If the node not selected and the key to the vector, key to the node is a minimum, then you will add it. You will keep that one. Okay, so you base a key is the different this one is a vector of integer for different outgoing node. Okay, we'll talk about it later. Where is the so there is another one is like eventually you have a function that you print the minimum spanning tree based on your graph. Graph is a vector of integer or vector integer. So this one is actually the adjacent matrix. That's your graph. And you also have the parents vector of this one. That's actually your root node. Okay, root node. Your starting root node and your graph. So based on that, you go the graph size and then you try to print it. Okay, you try to print it. So this one is your graph of the parents eyes eye. Okay, go to you actually starting from okay, whatever. This one will print your minimum spanning tree. So your main function is the prime algorithm. You keep your graph. You get the number B, okay, and you have parent V, okay, the store the constructed MSG. So this one is your minimum tree spanning tree. You store them into a vector parents. Okay, parents means that where it actually come from. Okay, so every node has a parent. Okay, and then key value is you the minimum wage from the cut. Okay, and the mean set is actually the included or not included. Some are true, some are false. Okay, Is that included in the minimum span tree or not included in the minimum span tree? Okay, but your input is your adjacent matrix. Okay. So based on this, you actually do the print minimum span tree algorithm. So right here at the end, you will print the minimum span tree. So this one is the final stage you print it. Okay. So basically, your main algorithm is that you get a vector of integer. That's your graph. Your graph described it as this, and then you try to find your prime minimum spanning tree with that graph. So this is the main algorithm. Okay. So from this main algorithm, you go into this prime minimum spanning tree algorithm. So you go into here, you given the graph, and then you create a number, that's V, that's the number of the node, okay? And then you have a way to store the constructed the minimum spanning tree, that's a parent V, okay? Parent that actually your parent node the number for each node, okay? And then key value to pick the minimum weight, so your each vertex edge, okay, that they had the minimum weight of edge, okay. And this minimum spanning set is included or not included set, okay. So from there, your initially all of your key I, okay, your connection to your node, everyone set to the maximum, and then every node is not included, okay. Now, okay, make key 0 as 0. So your first node, you make your node 0 as your first pick, the first node that you included, okay. And then it don't have parents, so you set the first one root, so no parent, okay. So after that, you need to update the key. Update the key means that when the minimum weight go into your set. So you do try to find min key given the set. So right now your minimum set right now should only have the node 0. That is true. The other one are all false, not included yet. And key value, you will try to find the min key with the key value. Okay, so key value right now, initially only the first node is 0. The others are what? The others are actually maximum. Okay, and then you start to work on the graph. So you do call min key. So you call min key, you go to the min key with the set condition of which node is including what node is not included. So basically, you go to every node again and make sure which node actually that is not included yet. Okay, not included. So not included yet, you actually try to find the node V is less than minimum. Okay, so minimum is there, and then you go to any key. Key is the node that has the minimum weight to that edge, to that node. Okay, so if you have something that you already found, then something that you haven't found. So haven't found, if there's an incoming edge, we call it key. And if those keys you find the minimum one, and then you will pick that node and include it. Okay. So you set the node that you pick and then set it to be true. And then you update your key and your parents. Okay, update your key and parents based on your graph. Okay, so to the nodes to update which one had the minimum value that you can go into an edge, you update your key and your graph. And based on this key and graph condition, you go back to do the minimum spanning tree calculation. So this one would finish the minimum spanning tree algorithm using the point algorithm. Okay. Okay, so this one, if you this, okay, let's actually look at it. The graph has a 5 node, okay, so basically your node 0 going to node 1 and 3, okay, go to 1 and 3. The weight is 2 and 6. Node 1 go to 0, that's 2, okay, you also go to node 2 with weight of 3. And you go to node 3 with weight of 8. And you also go to node 4 with weight of 5. Okay, so this is node number 1. And then node number 2, you have go to 1. You also go to 4 with weight of 7. And then you have node 3 that go to this sequence, this, and then you also go to node 4 with weight of 9. Okay. And then your node 4 connected with 5, 7, 9. That's it. This is the graph. Okay, so now you get started with your node 0 right here. You pick 2 to go 1. Then you have now you have this. Then you have 6, 8, 3, 5. You pick 3 to 2. Okay, now you have the 0, 1, 2. Then you have 9, 5, 7, 6, 8. So you pick 5 equal to 4. Now you only have 9, 6, 8 to pick. You pick 6. So with that, you actually will pick 0, 1, that's 2. 1, 2, that's actually 3. Then 0, 3, that's 6. Is it this one? And also 1, 4, that's actually 5. Okay? That's the minimum spanning tree. As for the minimum spanning tree, when we will use it, that's a different story. But at this moment, we just like depth first searching, we covered this different traversal algorithm. So this minimum spanning tree is another traversal algorithm. You actually spanning over different node with minimum weight. Is that okay? Okay, this is minimum spanning tree. Now, I actually don't follow the textbook, okay? I follow my own order. I'm not following the textbook. So now we have that. Let's actually look at also at the Krug's algorithm. So Prime's algorithm is every time you add the closer edge to it. So there's another algorithm called Krug's algorithm, minimum spanning tree. So this one is also a minimum spanning tree, okay, algorithm. But it's different from the point algorithm. It actually is also a greedy algorithm. Okay, it's still a greedy algorithm. So this one is very easy. You saw all the edges from the given graph. So let's assume that you actually have a different node. And I do have a spanning tree from where to where. I don't know. Right now, no node. So basically, let me sort in all of the edges that I have. And I have the understanding that if I found someone, say 1 right here, that actually minimum for all the edges, then I can have the assumption that this will be included in my minimum spanning tree, because if this one not used, then any other edge that would replace this one may add cost to my graph. Is that okay? Is that okay? By the way, minimum spanning tree, there is another actually idea you need to know. So let's assume that I have a 5 node. So no matter how I find the minimum spanning tree, since every time I add one node to my graph, so basically I have an n node. Eventually, the number of edge that I will pick is actually n minus 1. Just like previous one, I have a 5 node, but eventually the minimum span tree should have only 4 edges used. That's the idea, okay? That's the idea. So right here, same thing. That actually I use the outgoing edge of the existing node. So this one different. This one you pick the available edge that had not been used, and that also add a new node to the system. So right now, if I pick this one, then some of the edges that I will not consider, okay, if it doesn't bring the new edge to it. So you can check every edge in the system if it doesn't bring, if the post node already been occupied, then you kick it out. Then the rest of them, you pick the minimum one. So that's the solution 2. Then you will pick this one. After you pick this one, you actually keep the sorting of the different edges. But because the edges you sort the first time, second time you don't need to sort it anymore because the order should be the same because you just remove the edge that you already picked. Is that okay? You remove the edge that you already picked that's already picked, okay? And then you next one, you try to pick some of the node that you actually would add a new node to it. Okay. So this one you also need to keep a minimum spanning set and also keep the edges sorted, okay, in the priority queue, then that's it, okay. Okay, let's actually look at the graph, okay. Let's look at this one. Let's go back to the beginning part. So initially you have nothing. So over the map, I would say I'll pick 1 to 7 to 6, that actually is edge of 1. The next one, I think I'll pick this one, 2. I just actually pick an edge that actually from all the edge that will add one node to my system. This one won't add a node to my system. Okay, even though it's the same weight, but I cannot. Okay, actually you can also pick it. Let's assume that you pick it where is the minimum that you have. You can also pick this one, okay, but let's assume you pick this one. And then this one, you also pick this one. That's actually for sure because they are minimum. And then this one, you still look at it, which one is minimum. So you may pick this one, you may pick this one. There's a 4, okay, but it's okay. That's actually go. Okay, and then this one, go. Okay, and then anyway, these are actually right now. So you keep doing that until every node being covered and fully connected. Okay, next one. You pick 7. Okay. So this is 7 will not be picked because both nodes already being connected. So you pick the 8 one. Okay. And then this one you pick the 9 right here. This 8 will not be picked. Okay, and then you have every node being connected. So now you finish the algorithm. This one is called Kruskal's algorithm. Okay. Let's copy the code. So this Kruger one, again you have a adjacent matrix, okay, and you have different edges. Node 0, 1, 1, 3, 2, 3, 2, So that's actually to 0 and 1 with 10, 1 and 3 with 15, that's the weight. 2 and 3, that actually is 4. 2 and 0, that actually is 6. 0 and 3, that actually is 5. Okay, so basically, I think you pick this one, this one. This one will not be picked because it's actually connecting, making a circle. The two nodes have already been picked. Then you pick this one. That would be your Cusco minimum spanning tree. Okay? With that as the result, we can foresee, let's look at the Cusco minimum spanning tree algorithm. So this one, you will go to call this a Cusco minimum spanning tree algorithm. It passed the 4 and ages. I think 4 is the number of the node, okay? Ages is this adjacent matrix. So let's see. There is a class called disjoint set. Disjoint set is a vector of the parent and rank. Then that is a constructor. Parent is your parent set, okay? Rank is ranking, I think, who actually minimum weight. And there is a find function. And then there's a unite two node, connecting two node, okay? And then there's a comparator. So your Cusco minimum spanning tree like this, you would put in your age information and number of the node to there. So you sort every age that you have, okay? So there's a comparator is preparing for sorting. So you sort all the ages that you have. And that sorting result would be stored into your ages. So your age will be sorting based on the weight. Okay. So you created your do traversal on your disjoint set. So right here you have disjoint set. Disjoint set means the one set that you have data in there, the other one is not connected. Okay. Okay, so right here you try to find two node that actually is disjoint and then united them together and you plus weight into there. Okay, and you return the cost. So this one is a find and join function. So that actually is based on your data structure of this disjoint set data structure to join and connect. Okay, connecting different nodes. So that's the basic algorithm that you use for this Google algorithm. Okay, any questions so far? Okay, so these two algorithms, Prime and Kruger, will give you same result. Okay, same result. I personally like the Prim's algorithm because the Prim's algorithm actually is easier to understand and easier to code. Okay, easier to understand, easier to code. This Kruger a little bit more difficult. So that's why in the textbook, your textbook right here, it doesn't have the Kruger's algorithm. It only has this Prime's spanning tree algorithm. Okay, it only has that. But because these both algorithms are very well-known algorithms, so we still introduce them. Okay, we still introduce them. So Prime algorithm is based on your connected part, find the algorithm age that actually it actually is minimum. And then crew goals actually is you try to find a minimum one. Okay, so you don't edge that two node in the same set, that you won't use it. Okay, so basically you try to find the node that actually not connecting to each other. Okay, not connecting to each other, not in the same group. You try to find a new node based on the edges that you saw it. That's not disjoint. Okay, so that's actually the who's cause algorithm. Okay, so this minimum spanning tree can be used for this broadcast problem. Okay, can be used for this broadcast problem. So broadcast problem means that you have so many receiver or listener that you need to reach to. So by connecting which node can give you the minimum spanning tree. So let's assume that let's don't talk about this broadcast. Let's assume that these are different city. So you will connect every city. By each city to city, there is a construction cost. So if you want to build a network freeway system to connect every city, but you don't want to waste your money, then you can use a minimum spending tree. So basically, you can pick this one right here, this one right here, this one right here, this one right here. Maybe you will pick this one right here and this one right here. So in this way, you will connect all of the listeners using minimum spending tree. Okay. So it can be used for broadcast problem. It can be used for the connection of the cities, which is city or freeway system that will give you the minimum construction cost. Okay, that's usually is for that. So it's not used to show that from point one to point two to give you the minimum cost, but it give you the minimum cost for the overall city freeway construction cost. Okay. So usually this minimum spending tree problem is used to solve the minimum cost problem among cities. Is that okay?
Yeah.
So when you have some problem that you optimize to find a network that connecting every city, then you will use a minimum spending tree. So okay, so we demonstrate two minimum spending tree algorithm to solve the problem. Okay, right here primarily you need to know what is the problem and see right here they even don't have a code in this one. Okay, we just give you the idea of what is this problem and then why the minimum spending tree can solve the problem. Okay, and we also add one more solution of the Cusco algorithm. So there's a prime algorithm, there's a Cusco algorithm, and in standard data structure course, both will be covered. Okay, will be covered. So these are minimum spending tree. Now we are going to cover another very important topic that's called shortest path problem. Okay, that's called shortest path problem. And this shortest path problem usually is talking about this Dijkstra algorithm. I'm sorry. So this one is called Dijkstra algorithm. This one we're going to cover the shortest path algorithm, and then that's using Dijkstra algorithm. Okay, so shortest path problem is different from minimum spanning tree. So this one, shortest path problem is like we do have a network. Okay. I heard that you are with me or not. I heard that you hear me or not.
Yeah, I can hear you.
Shortest path problem, we talk about network. So in AP-CSP, okay, I'm talking about AP-CSP. So AP-CSP, we do talk about there's a node A to node B. So when node A communicate with node B, what happen?
The
How?
packets will get split up and they can all go different ways from point A to point B.
So if one of them is dead, what will happen?
Like if there's redundancy in the network, then that'll allow the packets, they can just take a different route to point B.
Okay. So this problem actually is called shortest path problem. So now, if I initially don't have any information, I don't have any information, then I have the weight of the communication set delay time for each one. I store in the network. I know that where to where should have how much delay. Then I find the minimum path from A to B. Then I connect it. This is called Dijkstra algorithm. So Dijkstra is used for here. Dijkstra is a person, is a professor, and he find the algorithm when he do communication, and he find the minimum path. So you connect from node A to node B. But in the middle, you send your data from A to the middle point. Let's assume that is a minimum node. You know, fine, is C. But when you arrive at C, but somehow your network actually break down. Now next one, when you are at the C, you will use the minimum spanning tree, shortest path algorithm to find a route from C to B again. But that would be with the runtime information of B and C already been dropped. Okay, so I'm combining AP-CSP and this course. So Dijkstra algorithm is wrong every time it go to a router to another node. Before you forward your information to the next node, you will calculate the shortest path. And then at the runtime, some of the paths may be done. Then you will actually find an alternative route to go through it. Is that okay?
Yeah.
Okay, so that actually is the idea. Then you will actually, so shortest path problem is actually invented by Dijkstra. And Dijkstra has two important inventions. One is this shortest path problem. The other one is the PMB process, the so-called PMB process. You actually do. Okay, here you have the Dijkstra algorithm. Okay, here you have the Dijkstra algorithm, and then Dijkstra, this person, Dijkstra, he has other important invention. Okay, this is a person called Edgar Dijkstra. He has another important invention is the semaphore algorithm that give you the security control, PMV process, okay, whatever. It's very important. So here you do have the shortest path algorithm. Let's see. Okay. Anyway, let's try to do this. Let's find a video to get the Dijkstra algorithm. Okay. I think they are good video you can find. Okay, let's try to see this whether this one work or not. Let's try in 3 minutes.
It takes courage to step into big shoes and still walk your own path. BS,
Today, I'm going to teach you how to run Dijkstra's algorithm on a weighted directed graph. Dijkstra's algorithm tells you the shortest distance from one node to every other node in the graph. This differs from prims and crusticles, which result in minimum spanning trees. Let's use the following graph for our example. We'll keep a list of unvisited nodes at the bottom. Our first step is to pick the starting node. Let's choose A. We'll use the table on the right to keep track of distances. Remember, the distances we are measuring are from our starting node, A. We put 0 for A and infinity for the others, as we haven't visited them yet. The next step is to examine the edges leaving A. We can reach B and C from A, so let's update the chart with the corresponding costs. Next, we look at the chart and pick the smallest edge of which the vertex hasn't been chosen. In this case, C. Let's cross off C in the unvisited node list, marking it as closed. After choosing C, we examine the edges leaving C and update the chart accordingly. B is now reachable from A with a cost of 3 by traveling through C. Also, D and E become reachable for the first time. Let's do the same thing as before, choosing the smallest path with an unclosed node. This time it's B. We repeat the process, examining the edges leaving B and updating the cost of getting to D and E. Now we choose D. This time there are no updates to our table, as there are no edges leaving D. Finally, we choose E. Again, there are no updates, but this time because the edge leaving E does not result in a shorter path. All the edges in the graph have now been visited and are closed. Here is the shortest path from A to the other nodes. The time complexity of Dijkstra's is big O of E plus V log V if a Fibonacci heap is used. Put simply, this is a result of creating the queue of distance values and looping through the edges of each node. Here's the pseudocode for Dijkstra's algorithm. For more information, please visit the source shown below in the description.
Okay, so this one actually is not really hard. It's actually a little bit similar to minimum spanning tree. Okay, so only thing is that
let's choose A.
This one.
The graph.
I'm sorry.
For print, let's use the following.
So you starting with the graph and you pick one node, and then you say that to here is actually 0, to other node everyone is infinity. Then you pick a minimum edge, and you go to a certain node, right? That's it, because that's minimum. So you assume that that is a shortest path. So this one represented shortest path from A to C only. Okay, it's visited, right? And the next one, that actually this one is 2 over here. So next one you are going to actually evaluate A to B. If you pass A to B, you update the minimum weight to B. Right now is maybe this one is 4, okay. And then minimum weight to C to B, this one maybe just 3. So it's minimum weight going to here now is actually 3, no longer 4. So this one will be dropped. You actually keep this one, your minimum weight. And then from C, you also connected to D and E. That's the first time you visited. So first time visited, you just go and update their minimum distance. So after that is being picked, then you continue to add until every node is visited. And then that will update to you the minimum cost to visit every node. Is that okay? So you keep updating the minimum weight, the minimum cost from A to each node until every node got visited. Then you will get your minimum shortest path. Is that okay? Okay, let's actually use a gig to gig 4 gigs. Let me do it this way. Okay, let's find this website first. Let me go to here and search it for. Okay, so this Dijkstra algorithm. So let's look at Dijkstra algorithm. So Dijkstra algorithm proposed by this Edgar's Dijkstra using for network connection. Okay. Okay, so let's look at this one. So initially you actually starting from 0, so actually the shortest path to 0 is nothing. Everyone else is infinity. Okay, you get started from here. Then you pick the minimum weight, so to connect 1, so you can guarantee that 1 will be connected with 2 as a minimum 1, and then you update after it being connected, then you update the minimum cost. So right here, it become 2 to here. And then the next one, you actually say, this one you update from the next one, your minimum cost to go to your 2 will become 6, your 3, you become 7. That you need to get started from 2, okay, including the one that go to 1. So that actually 3 becomes 7. And then 4 not connected, 5 not connected, 6 not connected. So that's up to update to there. You have the update for node 0, 1, 2. Okay, then you include in your node 2. So your node 2 actually right now should be 6. Okay, and then right now you actually update your cost to 8, 3, no update. 4, 5, 6, no update. Okay, and then you pick 3, given the fact you pick this one. So that one you actually have a still 7, you go to 3, but you right now you can update your 4 to be 17 and 5 to be 7 plus 2 is actually 22. Okay, and then you pick 3, and then you actually next one you will pick 4. And pick 4, you will actually update your 6 should be now 19. Okay, and your 5 right now still 22. So you will pick 6 first. Okay, this one up to here 19. And then next one you pick Y. Okay, then you get the every the updated. Okay, so you keep an unvisited node and the visited node data is that just like your minimum spanning tree set. Okay, and you also keep you updating your minimum distance for each one. So this one is considered to be dynamic programming and tabulation. You build it bottom up. So it actually is called tabulation of the dynamic programming because you update the minimum spanning trees cost on each run. So it's a dynamic programming and also it is a bottom up algorithm. We call it tabulation. Is that okay? Hello, is that okay?
Yeah.
Okay, it's given the graph as example, okay? So it show you step by step. First, you pick node 1, okay, and you update your different nodes, okay, to 2, 6, 7. Okay, that's what I told you. And then next one, you update different node, okay. Okay, go one by one until every node got visited, okay. Then actually your algorithm completed. So that's actually copy this one. Call it registrar, that's CPP, okay. So this one, you actually have a V and there's a graph. You add different edges to there and find the shortest path from 0. So let's actually look at your graph. So graph is a list of pairs. So this one is a list of pairs. This one is a list of edges. It's an adjacent list algorithm, number of node and adjacent list, and each one you have the edge, and you also have a function called shortest path. So here you have the constructor function, put in every edge in there. You go shortest path, each one of them keep track of the priority queue with the, okay, that's the priority queue. So those different queue is actually vectors that being processed. And then each one of them, you get a initial value of infinity for the kinetic cost. This is overall kinetic cost. Initially do that. And then you set the source node to be 0, that's your first node, your source node to be 0. Okay. And then while your priority queue is not empty, you go through the map to look at all the possible edges. And then you update the edge to there, you will see which one give you the shortest path updates. Okay, and at the end you show the distance. Okay, so you update your data. So this actually according to the algorithm we talked about. So these 3 algorithms that we mentioned today, covering the spanning tree, and also the shortest path algorithm. Okay, so shortest path algorithm is used when you need to find out there's a node from node A to node B. You want to get the minimum cost. It's called Dijkstra algorithm. Okay, minimum spanning tree is that you have a few cities that you need to connect. Like you would like to build a railroad system or you build a network system that give you the minimum cost. Okay, And then that minimum spanning tree has two versions. One's called Prime's algorithm, the other one is called Cusco's algorithm. Okay, so when you study this different algorithm, you just need to know about how the graph can be constructed and then their complexity. Okay, complexity. So when you pick that algorithm, how much complexity you will have. Okay, so that's the key idea that you need to have. Okay, anyway, today we try to introduce these three algorithms. Okay, and then next week. Okay, we are almost done with this course, and then next week we are going to work on the nice tour problem and maybe topology sorting problem and connected, strongly connected problem. So these are typical problems. Okay, so when you study this graph algorithm, first you know about how to construct a graph, and then breadth first searching, and then Dijkstra prime algorithm, you go to the shortest path or minimum spanning tree. Then you start to look at the problem solving, and then it's time you get started to go to the gateway or user code or problem to solve it. But user code actually is not organized as a graph problem, so I suggest you to go to gateway, so chapter 2. Okay, and we are going to do that. Okay, we are going to do that. Is that okay? Is that okay?
Yeah.
So after I finish this chapter, my plan is I will go to study the gateway chapter 2 for the silver to gold level for user code. Okay, that's our plan. Okay, today we are up to here. We just introduced these three algorithms. Okay, any question?
No.
No, I'll let you go. Okay, because all of you have many APs. Okay, good luck then. Okay, I try to cut short. Good night. Bye bye.
Bye. Thank you.
Thank you.
Have a good night.